Peter Adamson, and you're listening to the History of Philosophy podcast, brought to you with the support of the Philosophy Department at King's College London and the LMU in Munich. Online at historyofphilosophy.net. Today's episode, Metal More Attractive, William Gilbert and Magnetism. A pretty standard way of demarcating early modern philosophy, and the way I'll more or less be using on this podcast, is to say that it spans the 17th and 18th centuries. If we take this really literally, that would put the divide between pre-modern and modern philosophy in 1600. Imagine if they'd known at the time. They might have thrown parties to celebrate the fact that the Enlightenment was just around the corner. Of course, that didn't happen, but the year did see one publication that rather poignantly brings the story of pre-modern philosophy full circle. According to another standard historical convention, Western philosophy is assumed to start with the pre-Socratics, and in particular with Thales of Miletus. As you'll remember, since we just covered him a mere 434 episodes ago, one of the very few things known about him is that he said, "The magnet has a soul." And more than 2 millennia later, in that momentous year of 1600, William Gilbert published Concerning the Magnet, Magnetic Bodies, and This Great Magnet, the Earth, a new philosophy demonstrated by means of many arguments and experiments. Here we are after more than 2 millennia of philosophy, and we're still worrying about magnets. But we've come a long way, not least in terms of having more information to work with. Just that title gives us more information about Gilbert than we have for Thales' ideas about magnets. In fact, we can use the title of Gilbert's book as a handy guide to his innovations in the field of magnetism and electricity. Let's start with the phrase magnetic bodies. These had long been a subject of puzzlement and fascination. It was difficult on pretty well any pre-modern theory of matter to explain why a lodestone and a piece of iron should move towards one another. We see here what looks like spontaneous action, which is presumably what inspired Thales to credit the magnet with a soul. But we don't normally see this kind of motion in stone and metal. Rather, it seems to belong only to organic life, like when plants grow on their own, or when a cat moves with sudden and lethal speed in the direction of the sofa to take a nap. One exception to this rule would be that elemental bodies do naturally rise and fall, with earth and water moving towards the center of the earth because they are heavy, air and fire away from it because they are light. But that's clearly not what we're seeing with the magnet. Even more puzzling, magnetism seems to involve action at a distance, because the lodestone can attract the iron to it across a gap of space. That's very hard to explain by invoking the properties recognized in Aristotelian science, like heat or moisture. In antiquity, the Epicurean poet Lucretius tried to account for it in atomic terms. I mentioned this in episode 58, actually. His idea was that atoms are streaming off of the lodestone toward the iron and pushing air out of the way, creating a partial vacuum that sucks the two bodies together. But given that atomism was only just starting to revive around the end of the 16th century, this sort of explanation wasn't very appealing. Instead, magnetism was often recognized as one of many hidden or occult powers found in nature, like the stingray's ability to stun its prey or poison's ability to kill. You might recall the French doctor Jean Fernel and his treatise On the Hidden Causes of Things. Well, he mentioned the magnet, along with poisons and other similar phenomena, among the causes which stay hidden in the gloom of veiled nature. Gilbert thought he could do better by offering the new philosophy of magnetism mentioned in his title. One thing that was new was a theory of elemental bodies. In Aristotelianism, Earth is characterized by its dryness and coldness, and, as I just said, by its tendency to move downward. But once it reaches its natural place, it stops moving and indeed becomes entirely inert. Gilbert disagrees. He dismisses as ridiculous the idea that Earth is dead or a useless weight. Rather, all material bodies are full of native and inborn powers that cause motion. In a sense, he is still thinking a bit like Thales, in that he ascribes a vital force to the magnet, and not only to the magnet. Gilbert says that the pure element of Earth, which he calls true Earth, always revolves with a necessary motion and an inherent tendency to turn. Now, we never actually encounter absolutely pure elements in everyday life, but a lodestone, or a piece of iron, has a very high proportion of true Earth in it, which explains the tendency to come together as they join in the natural orientation and motion of this element. This is a rather daring proposal about the underlying chemistry of the lodestone and iron, since the former is, as its own title implies, indeed a stone, whereas the latter is a metal. How are we to believe that two such different substances are both close to being true Earth? Gilbert's answer to this question draws him into geological speculation. He thinks that metals form when vapors from deep within the Earth come together as juices that penetrate into other solid bodies. So the metallic properties of iron, which make it seem so unlike a lodestone, are just the result of the process by which it is formed. Still, both iron and the lodestone are made of the same stuff, namely true Earth with some impurities mixed in. All this implies that magnetism must be a far more pervasive phenomenon than we might have supposed. It isn't going to belong to just special stones that we occasionally dig up, for example in Magnesia, the region in ancient Greece that gives the magnet its name. Instead, all true Earth is magnetic. Which takes us to the next bit of Gilbert's title, the bold claim that the Earth itself is a great magnet. This brilliant insight was based, to some extent, on the discoveries of earlier authors. Back in the 13th century, a writer on magnets named Peter Peregrinus had already done observations of spherical magnets and noticed that they have poles of attraction. As you know, two magnets brought near each other will be attracted if oriented in the right way, but if you turn one of the two magnets around, they will instead repel one another. This already implies that magnetism is not just an indiscriminate tendency to attract things of the right sort. Rather, it seems to involve some sort of specific directionality. Then, in 1581, so about a couple of decades before Gilbert's treatise appeared, Robert Norman published a book called The New Attractive, a title I commend to anyone who is thinking of starting a fashion magazine. Norman described experiments with magnetic needles set upon corks floating in water. Norman found that the needle would settle on a certain direction and maintain equilibrium. Furthermore, he found that a magnetic needle dips slightly, with the tip of the needle slightly lower than its back end. In other words, the needle doesn't just aim north, but points right through the Earth, along a genuinely straight line between, say, London and the pole. Both phenomena suggested even more strongly that magnetism is not just a power to attract, but a tendency to be aligned in a certain direction. Norman assumed that his magnets were orienting themselves towards some target, which he called the respective point. But again, Gilbert disagreed. Magnets are not, like elemental bodies in the Aristotelian theory, trying to get to some natural place. They are just arranging themselves in the way that is natural for true Earth. In fact, Gilbert thought that strictly speaking, we should not say that magnets attract or are attracted by other bodies. That would imply some kind of compulsion, as if the lodestone were pulling iron towards it with an invisible string, or the pole were tugging from afar at the needle. Instead, Gilbert speaks of magnetic coition, or primary running together. Magnetic needles allowed to turn freely, like on a cork in water, will quite literally fall into line and point along a path which has the pole at its end. And when two bodies, made mostly of true Earth, are near one another, they will join together to cooperate in this effort. This is also how Gilbert explains magnetic repulsion. If you hold two magnets with their north poles facing, they seem to be pushing away from one another, but in fact, says Gilbert, they are just trying to turn themselves around so that they can get back into what would be a natural arrangement. Of course, magnetic orientation allows for the manufacture of compasses, which linked the research of Norman and Gilbert to the urgent practical question of navigation. No less than the astronomical interests of John Dee, Thomas Harriot, and others, research into magnetism was motivated by the demands of England's burgeoning projects in trade and colonialism. One of the scientific problems that arose in this context was magnetic variation, the fact that compass needles do not quite point due north. This was obviously very inconvenient for precise navigational calculation, so Gilbert and other theorists were doing their best to explain it, and if possible to correct for the variation. Thomas Digges, for example, surveyed observations about compass readings from different locations. But these suffered from inaccuracy, and he concluded in the end that with the currently available data, the problem was insoluble. All navigators could do is collect readings on local variation and tabulate the results. This information could then be used to adjust calculations made at any given place. Gilbert took a similar view, but added an explanation for the irregularity of the variation. The surface of the Earth, he speculated, has unevenly distributed deposits of iron, and the high concentration of true Earth in this ore can affect the compasses. Shortly after the appearance of Gilbert's treatise, this idea was rejected by the French cartographer Guillaume de Notonnier. He thought that iron deposits would never have an appreciable effect compared to the size of the whole Earth, so he proposed a different and correct explanation that the magnetic poles of the Earth have a location slightly different from the geographical poles. Letonnier did, however, agree with Gilbert on the more fundamental point that the Earth is a huge magnet. Gilbert called the spherical magnet that was so prominent in his experiments a terrella, literally a small Earth, and believed that he could extrapolate from the effects he observed to a literally global scale. The Earth itself has magnetic poles and is spinning on an axis that stretches between those poles, which is why we have the daily rotation that gives us night and day. Of course, this shows that Gilbert was working within a Copernican theory, according to which the Earth goes around the Sun once a year and turns on its axis each day. Indeed, some scholars assume that the whole point of Gilbert's theory was to support Copernicus. But we should be careful not to infer that all cosmic attraction was, to Gilbert's mind, attributable to magnetism. Remember, it's only true Earth and bodies made mostly of Earth that display magnetic properties. So the Earth and the other planets are not staying in their orbits around the Sun because of magnetism. And when you jump, it's not magnetism that makes you fall back down unless you are Michael Jordan. Instead, Gilbert speaks of a very broad phenomenon he calls electricity. Like the word magnet, this term comes from ancient Greek. In this case, it derives from electron, meaning amber, because you can rub amber and then use it to attract other small objects like, say, wood shavings. Nowadays, we explain this as static electricity, but from Gilbert's point of view, it exemplifies a general tendency of bodies to gather themselves together. This electricity is the reason the Earth holds together and explains the phenomena Newton would soon enough be accounting for with his theory of gravity. Cannonballs, apples, and most basketball players fall when they are up in the air because the Earth, says Gilbert, calls bodies back to itself. He no longer needs the Aristotelian idea of heavy and light bodies. And good thing, too, since in Copernican cosmology, the center point of the Earth is not in the middle of the universe. So it would make no sense to say that heavy objects are moving towards that point and light things away from it. A striking feature of Gilbert's arguments for all of this, one flagged in the title of his treatise, is that his theory is demonstrated by means of many arguments and experiments. The preface announces that the work is addressed to true philosophers, honest men, who seek knowledge not from books only, but from things themselves. Gilbert has gone to the trouble of adding asterisks in the margins of the work to indicate experimental observations, with the size of the asterisk corresponding to the importance of the observation. He is dismissive of what we might call armchair scientists, remarking that stronger conclusions arise from certain experiments and validated arguments than from probable conjectures and the beliefs of common speculators. The better part of a century ago, the scholar Edgar Zilsel made an intriguing proposal about this empirical dimension of Gilbert's work. He argued that the advances made by Gilbert were made possible by the closing of socio-economic gaps between the elite and the working class. No longer were scientists university scholars who never saw the outside of the library. They were now men of affairs who were out in the world and who met people who actually made stuff and worked with their hands. Surely, Zilsel speculates, blacksmiths and miners had been noticing magnetic phenomena, and surely this could have fed into the discoveries of scientists like Gilbert, who were curious about these same phenomena and were of sufficient education and social standing to publish what was being observed. The aforementioned Robert Norman might offer a good example. He was himself a craftsman more than a scientist who was simply building compasses before he started doing such experiments as mounting magnetic needles on floating corks. Zilsel's thesis is an intriguing one and could be fruitful for understanding what was to come in the 17th century. For that period, the most celebrated philosopher-craftsman would probably be Spinoza, who was a lens grinder. And without even going forward into the coming generations, we've already seen how important high-level craft skills were for the astronomical observations made by Tycho Brahe. Unfortunately, it's not clear whether Zilsel's hypothesis really stands up when applied to the case of magnetic theory. Norman explicitly said that he only started doing his experiments on the advice of certain learned and expert friends, so he arguably illustrates that craftspersons were not inclined to such pursuits unless encouraged by elite scholars. As for Gilbert, there is no evidence whatsoever that he was getting information from tradespersons. This is just a wild guess on Zilsel's part. Still, there was something important happening in this period. Even if the upper class scientists weren't getting ideas from the working class, they were increasingly doing careful empirical observation. We've seen this with Thomas Harriot and now Gilbert, and for a general statement of the method, we don't have long to wait, since it will famously come in the work of Francis Bacon. But if you're a regular listener, you're probably already expecting what I am going to say next. We should not get so excited about Gilbert as a harbinger of things to come that we forget to see him within his own historical context. I've already underscored the comparison between Gilbert and contemporaries like Dee and Harriot, and there are also resonances between his theory of matter and what we find in the Paracelsian movement. When he alludes to the fundamental principles of physical stuff, Gilbert mentions salt and sulfur, the basic principles of Paracelsus. Then, at a more abstract level, he thinks that we can isolate pure substances and analyze their natures through violent chemical processes, like melting and burning. Between this and his radically different understanding of elemental motion, we can say that Gilbert fits into the wave of anti-Aristotelian natural philosophy that was sweeping Europe at this time, as found in such diverse figures as Telesio, Bruno, Schenk, Sennert, Fanel, and of course the Copernicans. The Aristotelians noticed the new developments and tried to take account of them. A study of university disputations has shown that magnetism was already a fairly frequent topic of discussion in the 16th century, and that Gilbert's work started being mentioned in these events already in 1606. Of course, the scholastics persisted in invoking principles of Aristotelian physics, from substantial forms to the four elements and their natural places, even in the face of new theories like Gilbert's and an increasing tendency toward corpuscular theories like the one given so long ago by Lucretius. Like a light body in a heavy medium, ancient science wasn't going to go down without a fight. Speaking of fighting, another phenomenon, or supposed phenomenon, mentioned in these university disputations was the so-called weapon salve. This was a method endorsed by Paracelsus for healing wounds, in which one would apply a treatment to the weapon that caused the wound. Here was another case of action at a distance, at least for those who believed in it. As it happens, the thought of one man who did believe in it, and argued in its defense, also resonates with the other bit of doctrine we can ascribe to Thales, namely the primacy of water, which will, I hope, whet your appetite for the coming episode. Après cela, le déluge, because next time it's Robert Flood, here on The History of Philosophy Without Any Gaps.